Hey guys, welcome to the autonomic nervous system. You know, sometimes you stumble across these cartoons and they're just too good to ignore, so do yourself a favor and pause this and read it and make yourself a little bit happier. Alright, so what I have for you here is an image displaying a guy making a decision about what to do about a bear. And to be honest with you, this is not at all about this bear or any decision or what have you. What I want you to think about is how you feel when you are nervous, when you are in a altercation of some form, when you have a big decision to make. You have these dilated pupils, sweaty palms, your heart's racing, your blood pressure rises. All of these things taken together are an effect of your autonomic nervous system. And the autonomic nervous system is what we are doing today. Now, I changed this to a previous style slide, but it's all the same thing. I just wanted to stick to the same one we've been using this whole time. What I want to say is that we have already talked about your brain and spinal cord being systems, if you will, that allow us for integration of information. You know that you have sensory and motor divisions in your peripheral nervous system. The sensory motor division carrying information into the brain and spinal cord, and the motor division carrying information out from the brain and spinal cord. We talked about how we have somatic and visceral sensory inputs. Somatic inputs we are consciously aware of, like I can feel this table, that's a somatic input. Visceral inputs we are not as conscious of. For instance, like I can't necessarily tell what my blood chemistry is like at this very moment. That would be that would be a visceral sensory input. There we go. And by comparison to this, there are also motor outputs from the brain and spinal cord. These would be either somatic or visceral motor. Now, the only somatic motor output that you're capable of controlling is your skeletal muscles. Everything else falls into the realm of the visceral motor division, and the visceral motor division is what we call the autonomic nervous system. Okay? Because this is so complex, involving everything other than the skeletal muscle in terms of our motor outputs, this gets further broken down. The autonomic nervous system gets further broken down into the sympathetic divisions and the parasympathetic divisions. Sympathetic being thought of as rousing the body for activity, whereas the parasympathetic division is thought of as bringing you down, all right, helping you relax and calm the system so that you can digest a large meal, as a good example here. All right, so autonomos means self-governing. The autonomic nervous system regulates all homeostatic function. Okay, this is driven by the hypothalamus, regulating all homeostatic function. All of life's fundamental processes will be driven by the autonomic nervous system. Think about heart rate, blood pressure, ventilation responses, your breathing, body temperature, all of it. All of it, all homeostatic function is tied into the autonomic nervous system. Now, in this, there are certainly autonomic organs, effectors, if you will, and these are highly varied. Man, the autonomic nervous system, let me click over a few slides, it's got its hot little hands in all sorts of stuff, okay? Many systems are affected here, but we think of a few of these in particular. Like, for instance, I've got your major organs are going to be regulated by your visceral motor division. And again, note how I said that. Regulated. Okay, regulated. The idea is that the autonomic nervous system doesn't necessarily tell the body what to do. The autonomic nervous system regulates things that would be happening already. Let's talk about the heart. Why not? So, your heart has inset built-in pacemaking systems that keep the heart beating pretty much no matter what. Okay? What the autonomic nervous system does is it has the capacity to speed up that heart rate or to slow down that heart rate. Okay, the heart's going to beat regardless. What the autonomic nervous system does is it regulates how the heart beats. Yeah, that's perfect. That's perfect. Adjusts their activities based off of the body's changing needs. That's what the autonomic nervous system does. So, for instance, your eyes will always be able to perceive light, whereas the autonomic nervous system will regulate how much light can come into the eyes to be perceived. The autonomic nervous system controls your pupillary dilation and constriction reflexes. Okay. Speaking of visceral reflex activities, it's worthy to mention one really good one here. This is dealing with baroreceptors and the stretch response of your arterial networks. The basic concept here is that every time the heart beats, you go to ventricular systole, boom, the heart beats and it pushes blood out. Then the heart will relax, it goes into ventricular diastole, and it relaxes, and the pressure comes back off of the arterial network. So you get a pulse wave. Every time your heart beats, in reality what's happening is there is a pulse wave that goes through your arterial networks, stretching those arterioles in particular. As you stretch those arteries, as you stretch those arterioles, they have inset receptors called baroreceptors. Okay, baroreceptors. They can pick up the amount of stretch that's present there. Okay, so if there's too much stretch, they know. If there's not enough stretch, they know. And the amount of stretch in the baroreceptors basically sends a message to your brain. It helps your brain to interpret your blood's pressure. So if there's a lot of blood pressure, the stretch is increased. If there's not much blood pressure, the stretch is vastly decreased. So, what am I getting at? Blood pressure. Okay, so if your heart beats and the pressure's too high, your baroreceptors send a message to your brain and they say, hey, too much blood pressure, and the brain's response is to slow down your heart rate. Okay, so if the baroreceptor is picking up too much stretch, they will send a message to the brain. The brain's response is to slow the heart rate down. And in essence, by spacing out systole and diastole a little bit, by putting more space between contraction phases, it will decrease your general blood pressure. Okay, it's a long story, but that's how that works. You can decrease your blood pressure by spacing things out a little bit. Are you aware of this? No, because it's autonomic. Okay, this is happening behind the scenes. It is involuntary, it's regulatory, it's homeostatic. That's how the autonomic nervous system works. Okay, that is how the autonomic nervous system works. Output pathways. So the hypothalamus is in control. That's obvious. We've already said that. And I think we're now going to get into the nerves and sort of how they work. I invite you to read this. I'm just going to go straight to here. So in your somatic division, this would be like how you control skeletal muscle, for example. There is a single neuron. Okay, a single neuron that's going to allow for communication, or a single nerve, you might say, that's going to allow for communication between the spinal cord and the muscle itself. Okay, single nerve. That nerve is going to conduct impulses out through the length of this thing. It could be myelinated or non-myelinated, doesn't really matter. But the idea is that there's a single nerve. In the autonomic nervous system, there are two nerves along the way. Man, let me tell you, that's important. Okay, two nerves. So it's got a preganglionic and a postganglionic neuron with an autonomic ganglia in the middle. These two neurons in sequence with one another increase the complexity of the system, basically allowing you to have a tighter amount of control, if you will, over the autonomic nervous system. You see, these can be myelinated or non-myelinated. These can release different neurotransmitters. These have a plethora of different receptor types that are available. So the autonomic output pathway is very different from the somatic output pathway, because the somatic output pathway has a single nerve along the way, whereas the autonomic nervous system has a pair of neurons, preganglionic and postganglionic, along the path. The autonomic nervous system is broken down into two parts, parasympathetic and sympathetic. Feel free to read this. I'm just going to kind of shoot from the hip here. Again, we think of the sympathetic division of your autonomic nervous system as fight or flight, rousing the body for action, preparing you to do work, fear, anger, what have you. This would increase your heart rate, increase your blood pressure, cause bronchial dilation, which makes you capable of breathing better, and increases a breathing term referred to as vital capacity. It's kind of a long story, but increases your vital capacity a little bit. Increases blood glucose levels. So you put glucose into the bloodstream, and what this does is it will travel through the bloodstream, and anywhere you need more ATP, you can make ATP because there's glucose available. And by comparison, the sympathetic nervous system not only rouses all these structures, but it reduces blood flow to the skin, as an example. So if you are in a fight, the area of your body that might be damaged is probably your outer cutaneous membrane lining. In other words, your skin. So what you do is you limit blood flow to the skin in order to keep you from bleeding mightily if you are damaged. And alternatively, you also decrease blood flow to the digestive tract. You don't really care about digesting a hamburger if you're running from a lion and might be a hamburger yourself pretty soon. So what you do is you pull blood flow out of the digestive tract and you dump that into your skeletal muscles to increase your physical capacities, if you will. So this is all going to interplay with one another. And then, of course, there is the parasympathetic division. Rest and digest is the way we like to think about this. This calms the body down. What I like to think about when I'm doing this is the first time I ever went to my wife's grandmother's place for like Thanksgiving or something like that. She has like 20 people in the family over. They all eat this big meal, and then they all sit down and everybody sleeps like a rock. It's the craziest thing you've ever seen in your life. It's not the way things worked in my family, but it's the way things worked in hers. And you will see that this is a rest and digest reaction. They eat a big meal, they're in a safe location, so they lay around and they sleep. And it allows them to digest food more readily, so they can increase the blood flow to the digestive tract, take it away from the muscles and everything else. You lay there, you relax, and you digest your food. That is the parasympathetic division. Now, this is a gross oversimplification. Holy cow, is this inaccurate? The reality is that the sympathetic and the parasympathetic divisions are constantly working together to keep you in homeostatic balance. Your heart rate is a product of the parasympathetic division holding your heart rate down to a resting rate, and alternatively, if you need to increase your blood pressure, increase your heart rate, the sympathetic division will pull your heart rate up. These systems are constantly working together on all of these effectors. They're constantly working with one another all the time to keep you homeostatically balanced. It's not like you either are rest and digest or you're fight or flight. These two systems are constantly working together at this moment in you as you sit there, keeping you homeostatically balanced. Okay, keeping you homeostatically balanced. We call this dual innervation. Okay, dual innervation is how most of your bodily organs get both sympathetic and parasympathetic fibers. Okay, they get both. And in this, having, like, for instance, your heart or your lungs or your stomach getting both sympathetic and parasympathetic fibers, they can have either antagonistic effects or cooperative effects. All right, antagonistic effects simply means that they work against one another. The sympathetic division works against the parasympathetic and vice versa. Or alternatively, they can have a cooperative effect. This is where they both work together towards some unified or common goal. And it's going to look something like this. So, as I said previously, your general heart rate is held down by your parasympathetic nervous system, whereas in an emergency situation, the sympathetic nervous system has the ability to raise that heart rate. Your pupillary reaction, okay, this is also antagonistic. Your parasympathetic division will react to constrict your pupil in bright light, and alternatively, your sympathetic division will act to dilate your pupils in dim light. And this is also why you can tell, like a very scared person that's having a sympathetic fight or flight reaction. You may have heard the term, somebody looks like a deer in the headlights. The pupils get real big when you're scared. Or when you're lying or what have you, when you're nervous, the pupils dilate. And that's activity of the sympathetic nervous system, fight or flight. Yeah. Oh, and then, of course, there are cooperative effects. Cooperative effects are where we're working together towards some common goal. A really easy cooperative effect to talk about is how salivation happens. The parasympathetic division causes the release of serous saliva, whereas the sympathetic division causes the release of mucosal saliva. And you got to have both of these. You need the serous saliva to wet things and kind of help them to stay together, and then the mucosal saliva kind of wraps around everything and gives it this gooey lining, so when you swallow, things travel down your esophagus more easily. You gotta have both, and this is a cooperative effect of the sympathetic and parasympathetic divisions. Did I just skip around? Yes, I did. So we have talked about tone before. We established that you could start going to the gym and working out every day, and your spinal cord would start sending minor messages to your muscles to keep them in to keep them in a tonal state. You'll have muscle tone. Well, your sympathetic nervous system, man, parasympathetic nervous system, your autonomics, they have tone as well. Again, your resting heart rate is held down by parasympathetic tone. The parasympathetic nervous system is constantly sending messages to your heart, keeping it at a low normal rate of about 70 to 80 beats per minute. Whereas your arterioles that control your blood pressure and levels of general vasoconstriction and vasodilation, they are working entirely and uniquely off of the activities of the sympathetic nervous system. The basic concept is that if you want your blood vessels to be quite dilated, you send very few sympathetic messages, tonal messages. So the sympathetic nervous system is sending very few messages per unit of time to your blood vessels, and that keeps them quite dilated. And alternatively, if you send lots of messages per unit of time, you can cause the the smooth muscle inside those arterioles to begin to contract, and you can cause vasoconstriction. Okay, that will cause vasoconstriction. Again, vasoconstriction, increased firing frequency, it causes less blood flow, and then vasodilation is caused by decreased firing frequency of your sympathetic nervous system. And this is how we partition where blood goes. So we talked about how if you're having a fight or flight reaction, you can decrease blood flow to the skin surface. That's through the activities of vasoconstriction and vasodilation. Yeah, I'll take that. Prioritizing where blood goes, that's the sympathetic division. Minimizing bleeding if you're injured. So if you get cut or something like that, you will vasoconstrict the blood vessels that go to the area of damage initially to decrease blood flow. That's going to be sympathetic tone, vasodilation, vasoconstriction. Oh, dust, man. Alright, that'll work. We've already played this game. We've already played it. This is how we activate glands as well. So if you want a gland to produce more of whatever product it's making, what you do is you vasodilate the blood vessels that go to the gland, and you vasoconstrict the blood vessels coming out of the gland. And that makes a big pressure gradient internally, and that makes it produce more fluid, or what have you. This is done with aqueous humor in the eye, cerebrospinal fluid, paralymph in the ears. It's all the same. All the same stuff. Alright, you may remember from really early in the semester, you saw this slide about cholinergic synapses, sometimes being excitatory, sometimes being inhibitory. Well, we're about to go through and talk about this in a little more detail. It depends on the receptors, okay? That's really where we're headed. Alright, neurotransmitters and their receptors. How can different autonomic neurons have different effects? Well, the reality is that these different autonomic neurons can release different neurotransmitters, that's a fact. But sometimes the same neurotransmitter can have different effects on different target organs because they have different receptors. Sometimes your receptors are what we call excitatory. They rouse the system, make it more active. Sometimes the same neurotransmitter hits a different type of receptor, and that receptor is inhibitory. It decreases the function of a given structure within the body. Target cells respond differently depending upon what receptors are available. So let's go through and talk about these. Let's talk a little bit about the receptors and see where that sort of takes us. And again, let me point this out. This is somatic motor nerve. Yeah, the somatic division of your motor nervous system. Somatic has one fiber here, one nerve, whereas the autonomic nervous system has two in sequence, what's called preganglionic and postganglionic. And this is where I wanted to be. Alright, so what are we doing first? Parasympathetic. Okay, so parasympathetic is this up here. In the parasympathetic nervous system, what you'll find is your preganglionic neuron always releases acetylcholine. Okay, acetylcholine is secreted by all preganglionic neurons, so you'll see that here, here, and here. Always. Sympathetic, parasympathetic, doesn't matter. The preganglionic neuron always releases acetylcholine. There can be different receptors for it, but always releases acetylcholine. One moment. Alright, back on task. Sorry. kids and their needs for water. Where am I at? I don't even remember. So let's just roll through this and hope for the best. In the parasympathetic division of your autonomic nervous system, the preganglionic neuron releases acetylcholine, and so does the postganglionic neuron. All right. Parasympathetic division, the neurons, they all release acetylcholine, and they have two receptor forms for acetylcholine. These are called muscarinic receptors and nicotinic receptors. These are named after drugs that affect the receptors themselves. So muscarine is a derivative of a mushroom. So this drug that's used augments the function of muscarinic receptors, so we call them muscarinic receptors. And you can take a wild guess as to what drug can affect nicotinic receptors. All right. The idea is that muscarinic receptors can be excitatory or inhibitory. There are subclasses of these. So in some cases you release acetylcholine and it's excitatory. In other cases you release acetylcholine and it's inhibitory, even though they both have muscarinic receptors. And also there are nicotinic receptors. Nicotinic receptors are always excitatory. Okay, always excitatory. Nicotinic receptors are like those found on skeletal muscles. You release acetylcholine onto a skeletal muscle, it binds to a nicotinic receptor set, and it causes contraction. This is why acetylcholine can have varied effects on the body. Again, you release acetylcholine onto skeletal muscle, and it causes contraction. But you release acetylcholine onto cardiac muscle, which is almost identical to skeletal muscle in every way, except it has a different receptor type. And it's inhibitory. Acetylcholine is inhibitory on cardiac muscle because it's got muscarinic receptors, which are inhibitory. So it slows the heart rate down, in other words. Perfect. Let's go here. And then, of course, there is the sympathetic division of the autonomic nervous system. The sympathetic division will have its preganglionic neurons releasing acetylcholine, just like every other part of the autonomic nervous system. But in almost every single case, the sympathetic nervous system's postganglionic neuron releases a different neurotransmitter called norepinephrine. Okay, it's got a different neurotransmitter. These are called adrenergic fibers. They release norepinephrine, NE. And for norepinephrine, there are two different receptor types. These are the alpha adrenergic receptors and the beta adrenergic receptors. What I need you to know is that alpha adrenergic receptors are typically excitatory, whereas beta adrenergic receptors are typically inhibitory. And we will use drugs to deal with the function of the sympathetic nervous system in this fashion. So a person that's got a blood pressure issue, the blood pressure is just too high, what we can do is we can take drugs that block the receptors for the sympathetic nervous system to some degree. Depends upon how much medication you add. It's basically how much blocking there is. In some cases, these are alpha blockers for excitatory receptors. These alpha blocking drugs will cause the heart rate to change, cause blood pressure to change, and cause the person's general blood pressure to drop. Okay, so we can play games with all of this. Okay, we know what the neurotransmitters are. We know how the receptors work. So we can use certain medications to deal with this if we so choose. That's fine. So my main goal for you to understand here is that alpha adrenergic receptors are excitatory and beta adrenergic receptors are inhibitory, and that the sympathetic nervous system has a different neurotransmitter set than does the parasympathetic division. Yeah, we should probably talk about the diffuse effects of the sympathetic nervous system. So when acetylcholine is released, acetylcholine is immediately broken back down because we have a enzyme. You guys probably remember acetylcholinesterase. We have an enzyme that breaks down acetylcholine. There is no enzyme for norepinephrine. So what happens is when norepinephrine is released by the sympathetic division, it diffuses away from the synaptic cleft, wherever it is, and can cause all sorts of other body-wide effects. Basically, it gets into the bloodstream, and it causes other parts of the body to release norepinephrine, like the adrenal glands as a good example I'm providing here. And it takes a while to pull that neurotransmitter, which is now behaving like a hormone, out of the bloodstream. So it gets into the blood, and it takes a while to get it out. And this should be very obvious to you. Let me give you an example. Let's say that you wake up in the morning and you look at the clock and it's 9 and you're supposed to be at work at 9. You jump up and you freak out. You're like, oh my God, I got to get to work. And then you realize it's Saturday and you don't have to be anywhere. Can you just immediately lay back down and go back to sleep? No. It takes a little bit of time to relax again. And what you'll do is you'll feel your heart rate. It's like real fast, and it'll slowly, it'll slow back down and get to a resting state over time. What's having to go down there is the liver is basically pulling that norepinephrine out of blood supply and getting rid of it for you. So that the effects of the sympathetic nervous system are very long-lasting and body-wide. Sympathetic. That means together body or together function or something like that. I really forget. But the concept is that a sympathetic nervous system reaction will last a while, whereas a parasympathetic nervous system can go away immediately. Okay, because it's using acetylcholine, which is broken down by acetylcholinesterase. Unique roles of the sympathetic division. So, the adrenal medulla, your sweat glands, your erector pili muscles, your kidneys, and your blood vessels receive only sympathetic fibers. And because of this, that means that the sympathetic division can do some things that the parasympathetic division simply cannot. All of your thermoregulatory response is driven by the sympathetic nervous system. I mean, think about the concept, right? If your vasoconstriction and vasodilation are all driven by sympathetic tone, that means that the sympathetic nervous system controls vasoconstriction and vasodilation. It controls all thermoregulation. Your sympathetic nervous system controls the release of renin from the kidneys, which basically hormonally regulates your blood pressure. Your sympathetic nervous system can send your cells into overdrive and increase your general metabolic rate. I mean, there's just a whole host of things that goes on here, and a couple of those I want to talk about. The main thing that I will mention here is what's called recruitment synchronicity. Okay, you have heard stories of people in emergency situations that are capable of what you might call superhuman feats of strength or what have you. Those moments when you hear weird sounds in the other room and wonder what your kids are into. Anyway, recruitment synchronicity. So imagine if I'm trying to lift something heavy, I'm going to recruit muscle fibers and recruit, and eventually I can get a bunch of muscle fibers active and I can have great strength. But it takes a few moments for my muscles to get to that point of full-on recruitment to get maximal contraction out of my muscles. When you have norepinephrine, when you have adrenaline coursing through your veins, let me tell you something, folks. You have recruitment synchronicity. It causes your muscles to be on what we call a hair trigger. It allows them to have maximal flexion immediately. Okay, great strength on call the moment it's asked for. You got endorphins flowing through your system, so you don't feel pain. I mean, it's just different. Your body acts in a different way. Kind of reminds me of my Prius a little bit. I realize how dumb that sounds, but it's the truth. The Prius has a power mode button, and it kind of cracks me up, the Prius in its power mode. But what it does is it doesn't make the engine more powerful. When you put the car in power mode, it just makes it to where if you ever go near the gas pedal, if you touch the gas pedal at all, man, it just floors it. Okay, just totally floors it right out of the gate. So it feels like, oh man, the car's really responsive now. That's what recruitment synchronicity does. When you're in an emergency situation, you want your muscles to be able to generate maximal flexion very quickly. And that is done by the sympathetic nervous system. In fact, I predict our buddy Bruce Lee here. Bruce was not the strongest guy on the planet, was not the biggest guy on the planet. What he was incredibly fast. My prediction is that he had a good grasp on this autonomic function and had the ability to develop this recruitment synchronicity into, very good martial arts technique. And I'll mention one more comment. That's shaky speech. So you may have heard me talk about there's a girl I watched at a scientific gathering one time, and she was giving a talk on what are called cofferdams. And she just had the hardest time getting her words out, man. She just couldn't get the words out. And the reason for that is very simple. Like, I can sit here and talk to you with very smooth speaking because I'm not at all worried about this. I'm not nervous or freaking out or anything. So my diaphragm, I have really good control of it, and thus very good control over the volume of my voice. If I was scared to death, like that girl that was given the talk about cofferdams, man, You just can't regulate the diaphragm as cleanly as you can otherwise. You end up with recruitment synchronicity. So you're either like, you just can't get the words out, or you're yelling at people because you're either flexing the diaphragm fully or you're not really moving it at all. That is recruitment synchronicity. Now, a few more comments. The hypothalamus is certainly in control of all of this. All right, it runs the show. There can be influences from like the limbic system because the limbic system wraps around the hypothalamus. Your cerebral cortex is very important for the whole function of the brain, so it can have some level of influence. But what I need you to understand is the hypothalamus is the boss. The hypothalamus is the boss. There can be other influences. There are certainly other influences, but the hypothalamus runs the show. Okay, the hypothalamus runs the show. Let's talk about it a little bit. Let me see how far I want to go here. Okay. Powerful emotions. Let's just jump straight down to there. Imagine that someone is about to give you some terrible news. The first thing they tell you to do is sit down. Because they're afraid that if they tell you this bad news, you're going to pass out and you're going to hit the floor and get hurt. Why would you pass out? There's no reason to pass out. The reason that you pass out is because of this hypothalamic regulation. So if you get really terrible news, the limbic system freaks out. And if the limbic system freaks out, it has the capacity to augment the function of the hypothalamus, which controls all homeostatic function. And your your heart rate might drop, your blood pressure might drop, and you'll pass out from that. All right? This can happen. In fact, we can see this. We can see this constantly. You see good food on TV and your mouth waters. That is a cortical influence over the hypothalamus. All right? You think about a loved one that you miss and your heart starts to beat faster. All of this plays in. So let me make sure that I hit the high point here. The idea is that the hypothalamus is in control, but there can be influences from elsewhere. And in fact, we kind of learn to control this a little bit. I've seen where people are hooked up to a computer, and basically the computer measures their heart rate. And if their heart rate rises, it's like a game. There's like a basketball goal, and they shoot the basket on this game. And if their heart rate goes up, the ball rises. And if their heart rate drops, the ball drops. And they get pretty good at getting the ball in the hoop. Like after an hour or two of playing the game, you get to where you can kind of mentally control your heart rate a little bit. That is a cortical influence. This is what's called biofeedback training. So the hypothalamus is control. The hypothalamus is in control. But the cerebral cortex and the limbic system, they can influence this a little bit. Okay, they can influence a little bit. That'll do. And then, of course, there are a few imbalances of the autonomic nervous system that are worthy of our consideration. Hypertension is high blood pressure, so anything over like 150 over 90 or something like that is considered high blood pressure. And this is very easily treated with alpha-blocking drugs to decrease heart rate. And you can drop the blood pressure right out the bottom if you want to. Raynaud's disease is where you have undue vasoconstriction in the fingers in particular, and what will happen is these will go cyanotic and they'll hurt real bad from a lack of blood flow. Basically, if you decrease blood flow to an area of the body, first it goes numb and then it starts to hurt. That's why if you've ever fallen asleep on your arm and you wake up and it's numb, what woke you up is it was starting to hurt. Okay, when you decrease blood flow, that's what happens. This is a bad situation, man. What they oftentimes will do is they'll go down and cut the sympathetic nerve fibers that go to the fingertips. This is called a sympathectomy, and it augments the way that vasoconstriction and vasodilation work. I've seen where people with this disorder have used topical nitroglycerin ointments and things to cause vasodilation. It's just no fun. And frankly, I think that's good enough. I think that's good enough for us and our purposes at this moment. So let's stop it here, and we'll pick it up on the next one. Thanks, guys.